All right, so when we hear the word death, we often associate it with loss, the end of something good, chaos, and destruction, seemingly like the very opposite of life. However, today I want to challenge this perception and show you how death is not only an essential part of life, but also what makes life possible. Imagine you're a sculptor with these solid blocks of stone without any form and shape. All you have is a blueprint, a vision of what this stone could become. And to bring that vision to life, the sculptor must begin removing large sections of the stone. Chiseling away the unnecessary materials would gradually reveal the sculpture. This process mirrors the creation of life itself, called embryogenesis. The building blocks that makes up all living things are called cells, and during embryogenesis, the cells rapidly proliferate to form our organs and tissues. However, ironically, cells also undergo death. They don't die one at a time or two at a time. They undergo large-scale cell deaths, eliminating millions of cells in a timely manner to sculpt our tissues and organs to their appropriate forms. For example, the separation of the digits of our hands and the formation of tubules, and also the segregation of the anatomically distinct muscle masses of the human body. Cell death during embryogenesis is a highly coordinated process occurring in specific regions at precise times and in specific patterns. This raises a fascinating question of how is cell death coordinated in space and in time to sculpt the complex and functional structures that are required for life. In my study, I found that this is made possible through propagating waves of cell death. And let me show you how. Here I perform time-lapse imaging on a monolayer of cells. Here each blue dot represents a single cell, and when a cell dies, the blue dot will light up to become color white. So let's focus on this region where you will see cell death initiate and propagate across the entire cell population. We next ask, what can be the signaling molecule or the message that cells pass on to their neighbors, making cell death to be so contagious? And I found that there is a signaling wavefront here shown as the yellow color that moves ahead of cell death. This yellow wavefront here represents lipid reactive oxygen species, or lipid ROS here, that transmits between cells and causes cell death. And what's really remarkable here, really for me, is that the cell death propagation is propagating at a constant speed as indicated by the constant progression of the cell death boundary. This type of cell death is what we call ferroptosis, mediated by the accumulation of iron and reactive oxygen species, and we found that ferroptosis can propagate at constant speed without any signs of slowing down across long distances. This is a phenomenon we call trigger waves, and by nature, trigger waves can propagate infinitely across space. So how can biology utilize this spatial infinite propagation of cell death to eliminate unwanted cells only without causing damage to the entire organism? We answered this question using the chicken embryonic limb as a model system. So here, as the limb develops, this is the limb. We did time-lapse imaging and indeed found that there is propagation of cell death, and it is spatially restricted to the central region only. And cells at the lateral region, they remain viable. And we found that this spatial restriction is because the fuel for cell death, which is the oxidizable lipids, they are spatially patterned in the limb so as to confine cell death to this specific region. And we found that this cell death is essential, is important to separate the two distinct muscle mass of the limb, which is the foot and the shank. So all of these data have been published, and you can check it out if you're interested. But I want to switch gears here for a little bit and share with you about this exciting possibility of harnessing these propagating waves for cancer therapy. We know that one great challenge in cancer therapy is the presence of partial drug response, which would lead to cancer recurrence. So indeed, in our experiments with kidney adenocarcinoma cells, when we treated it with chemotherapy drugs and measured the cell death percentage in the y-axis over time, we find that cell death could only reach maximum of like 70%, leaving substantial portion of the tumor intact. However, when we treat the cells with ferroptosis inducer Erestin, we see this rapid rise of cell death that eliminates 100% of the cell population. And this is owing to the propagative nature of cell death. So I really look forward to brainstorming with the great minds here to explore this possibility of harnessing these propagating cell deaths for cancer therapy. So with that, I want to end my presentation here, and thank you for your attention.